OSIRIS-REx, Asteroid Redirect, and Mars 2020. Question and answer panel and questions from the audience is encouraged during this. I'm Charlie Price. I'm the moderator, and I will introduce all our participants here in just a moment. Okay, this is the agenda that we'll be going through. We'll do an introduction. We'll talk about the panel purpose and objectives, the discussion assumptions. Then we'll talk about 3 missions: the OSIRIS-REx mission, the Asteroid Redirect mission, and the Mars 2020 mission. Then we'll talk about vision systems associated, vision systems that are associated with the missions, or we expect to be associated with the missions. And then we'd like a lot of questions, and we'll provide answers from the audience, both online and in the room, and then we'll have a wrap up and take away. Okay. Our panelist today starts with Andre Sylvester at Johnson Space Center. Andre is a graduate of the University of Texas, and he's the Assistant Division Chief of the Robotics, Software, and Simulation Division at NASA JSC. Andre is also leading the asteroid capture system studies that are ongoing for the Asteroid Redirect mission at the Johnson Space Center. I've known Andre for probably 25 years. I remember when he was a fresh out new hire at JSC. And over the years, I've always been impressed with Andre. But one of the things I want to share with you is that Andre and his brother Andy can do a very good impression of the Blues Brothers. They're both very good singers. Okay. Also on our panel from here is Dr. Thomas Evans. Thomas earned his PhD from West Virginia University and is the West Virginia Robotic Technology Center Research Program Manager. He's also a professor of mechanical and aerospace engineering at West Virginia University. And we're glad you're here today, Thomas. Also on our panel is David Turner, also a West Virginia University grad. He's been with the IV&V team for a little over 2 years. He's a team member through the Newbold company, and he's worked robotics capability development and developed the Visio-based technique of displaying layered scenarios of nominal and fault and failure cases for the analyst. And he is now working as an analyst on the OSIRIS-REx mission. Vincent Howard, who joined us this April, graduated from the University of California at Berkeley and Santa Clara University. He has done graduate work at the University of Hawaii, and he was a member of an underwater remote operated vehicle robot team on multiple NOAA expeditions in the Western Pacific, and he's now a robotics engineer here with TASC. I kid Vincent in that he obviously got tired of all that wonderful good weather in California and Hawaii, and he wanted to come to West Virginia and find out what real weather was all about. And then finally, for myself, I joined NASA JSC in 1963 and have been working for NASA in one way or another ever since. I worked Apollo, Shuttle, Space Station, and what I like to say is I did start the robotics branch at JSC, and one of the things that we did under my watch is put together the first version of Robonaut. It wasn't called Robonaut in those days, but it was the humanoid. And now I'm the TASC robotics lead here at IV&V. Okay. This panel will discuss the robotic components of 3 NASA missions currently under early development. And by components, I mean the mechanical, the sensory, and the autonomy components. The three missions are the OSIRIS-REx mission, which is a robotic mission to land on an asteroid and return samples to Earth. The Asteroid redirect mission, which is a robotic mission to move an asteroid to lunar orbit and follow it with a human mission to deliver asteroids to perform science on the asteroid. And the Mars 2020 mission, the next Mars rover mission, which will be similar to Curiosity, but it'll have different science objectives. We'll go through these charts. I've got embedded questions in the charts for each of our panelists, but we also invite questions from the audience as well. And we will have a session at the end for Q&A. Okay, the discussion assumptions. Let's talk just a little bit about how these missions will be set up. The asteroid for OSIRIS-REx has already been determined. It's asteroid Bennu, and it was, and the asteroid for the redirect are selected under a long study process using a variety of space-based and Earth-based telescopes to determine the orbital parameters of the asteroids. For example, the energy level, the perihelion, the aphelion, as well as their spin, mass, inertia, and albedo, or the amount of light that they reflect. And before the mission is launched, we have a good geometric physics model of the target asteroid based on all this observed data. So you don't just wander out in space and pick an asteroid. You know a lot about it before you get there. And similarly on Mars, the landing and exploration for each Mars mission, including the next, is going to be selected on years of observation by terrestrial and space telescopes of the Mars surface, also by the Mars orbiters that are going around Mars. And there will be a very precise topographical map of the area, well defined, before the mission is ever launched. And I'm speculating, but I don't want to represent something without knowing it for a fact, but I'm speculating that this topological map would be available through the onboard vision system. However, uncertainties in these parameters for all of these missions require that we have sensors on the spacecraft or the rovers to refine the knowledge of the state information of the targets relative to the actual spacecraft control systems. So that's what we're going to talk about when we talk about vision systems. Okay, now I want to turn it over to David to talk about the OSIRIS-REx mission for the next couple of charts.
All right, thanks, Charlie. Just a little bit of background on the OSIRIS-REx mission for those who aren't familiar with it. It's being developed by Lockheed Martin and Goddard. It's set to launch in September of 2016 with a plan to rendezvous with the asteroid Bennu in 2019. Once it gets there, it's going to map the surface using cameras, spectrometers. It's going to define the thermal properties. While it's there, it's going to collect a sample by touching down on the surface and collecting a sample using the TAGSAM sampler head. Part of the science at the asteroid is to determine the thermal properties of it, so that we'll better understand the Yarkovsky effect. It's basically the cyclic heating and cooling of the asteroid can actually alter its orbital properties. And since this asteroid could possibly collide with Earth sometime in the next 2 centuries, it's particular interest to figure out how the Yarkovsky effect will actually affect its orbital properties. And then the mission wants to return the sample that it collects to Earth by 2022. Okay. So as I mentioned, the sample for OSIRIS-REx will be collected with a TAGSAM sampler. It's a robotic manipulator. It's a 3 degree of freedom, but it's limited to planar motion. So it's really kind of like a sort of a upper arm, lower arm, wrist type deal with 3 stepper motors as hinge joints. The end of the sampler head is the the end of the robotic arm is the TAG-SAM sampler head, which is a cylinder that is placed down on the surface of the asteroid and forces nitrogen gas into the dust on the asteroid to collect it. The control of the robotic arm is going to be done using open loop operations. As the sampler head comes into contact with the surface of the asteroid, the hope is that it comes down on a relatively flat spot so that it creates a solid interface between the sampler and the surface. If it comes down on a rock, it's possible that the sampling attempt could be less than nominal, and some of the nitrogen gas won't be able to be utilized to drive regolith from the surface into the sampler head. So hopefully the hope is that with enough mapping, visual mapping ahead of time, that they can pick a sampler site without obstructions that would prevent the sampler head from getting a good plant against the surface of the asteroid. There are other articulated mechanisms on the OSIRIS-REx spacecraft, one of which is the sample return capsule, which is on top of the spacecraft, has a articulated hinge to open and close it. So once the sample is successfully collected from the surface, you're going to open the sample return capsule and place the sample inside it and then close it down again. The sample return capsule uses the same principles as the TAG-SAM arm. Open loop control using stepper motors. And then also the spacecraft has articulated solar arrays. Primarily, they want to be able to move the solar arrays away from the surface of the asteroid whenever they go down for sampling to reduce the risk of dust contamination when they're that close to the surface. As far as the sensors that are going to be on the spacecraft to help it perform these robotic behaviors, there are vision and ranging sensors that it's going to be used to help guide the spacecraft down to the surface. As far as vision goes, it utilizes a SAMCAM, a sample camera, which will help it position the TAG-SAM arm. Since it's open loop control, they'll be able to use pictures to verify that the TAG-SAM arm is where they want it to be before they attempt to sample. As it's going down, they're going to use GNC LiDARs to obtain range information and give them a better idea of when they're close to the surface and when they need to be ready to fire the nitrogen to collect a sample. Since the OSIRIS-REx, the asteroid that this is visiting, Bennu, sort of floats around in the orbits between Earth and Mars. So when the OSIRIS-REx spacecraft gets to the asteroid, it's going to be a pretty good distance away from Earth. I think during the sampling operations, it's going to be, as far as like a real-time commanding goes, it's going to be about 15 minutes away or 30 minutes away round trip. So given this reality, it's impractical to teleoperate the spacecraft from that distance, just due to the delay and the critical nature of touching our billion-dollar spacecraft down onto the surface of a big rock. So the entire sampling operation is going to be scripted ahead of time using sequences, and then the spacecraft is going to have the autonomy necessary to determine if a sampling attempt is going to have a good chance for success, and if it is, to take the actions necessary to fire the nitrogen and then safely back away from the asteroid. Or it's going to have the autonomy to determine if a sampling attempt is not going to be successful, so it can back away from the asteroid prematurely and let the ground know that there was a problem, and then the ground can sort out the particular details once the spacecraft's a safe distance away from the surface of the asteroid.
Okay, so here's a perfect example of the distance is so far away that we have to rely on the autonomy of the system.
Yeah.
Yes. All right. And I'm going to quibble just a little bit. And it seems like I remember that there was a passive fourth joint that acted as a shock absorber when you come down.
Yeah, there is
a spring compression joint there.
Yeah, there's a compressive spring on the sampler arm so that whenever it contacts the surface of the asteroid, it can absorb the impact, so you're not getting that rigid sort of jarring collision once you make contact with the surface. And then since you have that compressive joint, it actually allows you, if you get a good seal between the sampler head and the surface, it allows you a few seconds of guaranteed contact during which you can perform the sampling and collect the dust using the nitrogen gas.
Okay, and is there something about a 10-second countdown timer that once you have contact, you start a clock that after 10 seconds you fire the jets to go up?
Yeah, once the range, either from the LiDAR or some other system, determines that the spacecraft is close to the surface, that's when it'll arm itself for sampling. And then once it determines that it has made contact, it will fire the nitrogen gas, and then it will set a back away timer. And then once the timer expires, it will fire the thrusters and back away from the surface of the asteroid. And then it will continue backing away until it's about 10 kilometers away, and then the ground will begin analyzing whether or not they retrieved enough sample.
Right. And as I remember, after the sampling, the process that you will go through to inspect the outside of the sampling head and determining the mass of the interior, and also the constraint that you have to keep the sampling head in the shadows, lest the volatiles, materials that you've sampled might get too hot.
Yeah, once the sample has been collected, they will slew the spacecraft into the sunlight and move the sample head around in front of the SAMCAM, take pictures to determine if they can see that there's regolith inside the sampler head. But once this is completed, it's necessary to slew the spacecraft back out of the sun and hide the sampler head from the sunlight, so that you don't risk damaging any of the sample you've collected due to heating it up too much.
And the imaging that you do in that case is beamed back to Earth and is examined on Earth rather than any kind of autonomous.
Yeah, there's no, in that situation, there's no image processing on board the spacecraft. It's simply taking pictures per the commanded robotic arm position, and then it's sending them back to Earth, and then analysts on Earth will determine if the sample is present in the pictures.
Right. Okay, we'll go to the next chart. This is chart 8, and this is Andre's chart about asteroid redirect.
Thank you, Charlie. Can you hear me? Hello, Charles. Can you hear me? Charles, can you hear me? Can y'all hear me on the loop here? Okay, very good. So the asteroid redirect mission is a new initiative that NASA formulated over the last year and a half or so to respond to the National Space Policy guidance for NASA to develop missions to explore near-Earth objects and near-Earth asteroids. And this approach for doing that exploration allows us to leverage our knowledge of robotic systems as well as our characterization of near-Earth asteroids, and try to bring an object closer to Earth in order for us to more easily access it. There were some studies that looked at sending crews out to distant asteroids, but the logistics were too challenging. So this looks like a more feasible concept. In this mission, as Charles mentioned earlier, there is the looking for and the finding of candidate asteroids, and that's done with ground-based and space-based observation. Once a target asteroid has been identified, then a redirect vehicle would be sent out to try and retrieve the asteroid and then return it to a high lunar orbit. And so what you see in this chart are two concepts that the agency is exploring associated with that retrieval activity. The one in the upper left, designated as option A, is intended to capture an entire asteroid on the order of 4 meters to 10 meters in diameter. And then once it's been captured and stabilized, then return that asteroid to lunar orbit called a distant retrograde orbit, which is very stable. And once the rock has been placed in that orbit, the spacecraft as well, then it should remain there for quite some time. In addition, we've looked at an option B consideration where we send a similar spacecraft to a larger asteroid, maybe 100 kilometers in diameter or along its major dimension. And from that asteroid, pluck a smaller boulder, maybe on the order of 1 to 2 meters from the surface of the asteroid, 1 to 2 meters in diameter. And then take that retrieved boulder and return that to the distant retrograde orbit around the moon. So in that depiction, you see a lander-like construct in this picture where we have a truss frame type legs that serve as the landing legs for landing on the asteroid, and then a second set of truss-like legs that can essentially scoop up the boulder from the surface. In this particular concept that you see here, once the boulder has been secured by the inner set of truss elements, then the landing truss elements actually would use an actuator to push off the asteroid to achieve an initial separation. And then once they've separated from the asteroid, then they would return, would start using their RCS and propulsion systems to do the return to the Earth-Moon system. As opposed to option A, which uses an inflatable structure concept, which is then retracted around the asteroid and then secured against the spacecraft. So those are the two basic concepts that the agency has been exploring for bringing the asteroid back to lunar orbit. And then once it reaches lunar orbit, we would send a crew ranging from 2 to 4 crew in size, depending on the option, using the Orion spacecraft on the Space Launch System booster. And then they would go out and visit the asteroid and collect some samples and do some science activities. So that's the mission in a nutshell.
I've got some questions there that if you can respond to, please.
Sure. So again, the mech. Hold on, I've got a little echo here. All right, so the mechanisms from the chart before, for option A, we're looking at an inflatable bag-like structure, which would be deployed, of course, with an inflation gas and then retracted with a series of cables and winches. With the picking of the boulder, we would be looking at the either a truss frame structure as the one you saw there. We've also looked at 7-DOF manipulator arms that could be mounted on the spacecraft and utilizing attachment mechanisms. So anyhow, those are the two different types of mechanisms or approaches to achieve the rigid interface. And then once we've got that rigidized interface, there really isn't any, at this moment, not any mechanisms required for that are based on the return vehicle for the scientific and engineering investigation. What we envision right now is that the crewed mission will be bringing the tools and capabilities to do the investigation of the asteroid once it returns to lunar orbit. So hopefully that answers your questions. Hold on.
Do you have any idea of what the kind of sensors, such as cameras or laser rangers, that would be used to drive these mechanisms?
Sure. So there are a range of sensors that will be employed during the mission. One, as the spacecraft is arriving in the vicinity of the asteroid, we'll be using cameras used in combination with optical navigation systems, so narrow field of view cameras at about 50,000 kilometers to guide the spacecraft into a close proximity. Once we're within about a kilometer, we'll be using a combination of either a LiDAR or infrared camera or a laser rangefinder. We're still doing trades on the different sensors for the near close-in observation of the asteroid, and we'll be doing a lot of characterization as we get in closer. Then once we get to the once we get in within range for the capture, we'll be relying primarily on cameras to provide that characterization that you talked about earlier. And much as your first speaker mentioned, we'll be using scripts to allow the spacecraft to basically execute the capture. Because of the long distance, it's impractical to be able to control it and on a real-time basis. So we will also be using a scripted autonomy capability based on all the data gathering. And once we've decided that the proximity is proper and the conditions are right, then the spacecraft will be given the go to execute a script and conduct the capture and stabilization autonomously. And so that's a key feature for our mission as well.
Okay, we'll go on to the next chart. And this is a rendering of the Mars 2020 mission. We talked about it in the previous hour, but I'll go ahead and repeat. The mission is similar to Curiosity in that it will be a rover using the same kind of descent and approach, entry, descent, and landing approach. The rover is 40% lighter due to the fact that a big part of the mission is to collect and cache samples for a future mission to return them to Earth. So that's a major difference in the function of between it and Curiosity. And from an optical standpoint, the cameras you have the hazard cameras both in the front and the back down at the below deck level to prevent collisions with rocks or craters. But up on the mast, in addition to the fact that you'll have two stereo pairs of long distance cameras to do triangulation for navigation, this rover, Mars 2020, will have a zoom feature that Curiosity did not have. So it'll have a farther reach with what it can do for its navigation. And it was pointed out by one of our questioners that the entry through landing on previous Mars rovers have had a camera system for determining altitude or distance downrange. And I would fully expect that kind of a capability to also be on this mission, although I cannot speak authoritatively on that. Okay, going to the next chart, I asked myself some questions. Okay, so what are the mechanisms of this Curiosity class rover? Well, it's got 6 wheels for stability. It's a tried and true rocker bogie design that has been on the last 6 or so rovers that have done so well on Mars. The back 4 are ganged together in independent articulations with two additional motors, wheels in the front. They all drive both directions, and the 4 on the corner, so to speak, the front 2 and the back 2 steer. Mounted on the platform is a 5-degree of freedom manipulator arm that can reach approximately 2 meters reach. And for Curiosity, it rotated a turret to position and preload tools and instruments. This is key to performing all the different kinds of science. So you had a tool for drilling, a tool for scooping, a tool for other functions on that turret, science or or instrumentation on that turret. For Mars 2020, there will be different science instruments for different purposes, and probably there'll be a lid on the container that you put the cache rocks in, similar to the function on OSIRIS-REx. Again, speculation on my part. And what kind of sensors? Pointed out the redundant stereo pair on the mast and the hazard cameras on the front, pair of them, or rather 2 pairs of hazard cameras on the front and 1 pair in the rear. And I maintain there would be a significant amount of autonomy to make the maximum use of the daylight hours on Mars. In talking with the GAPL folks about planning the missions, they do, on Curiosity, they do uplink a plan, a full day's plan, or a full plan for multiple days will be uplinked and then executed. And then when Mars does get in conjunction with the Earth and we lose contact with it for 2 to 3 weeks, there will be a full plan uploaded prior to conjunction to be operated autonomously while we are not in contact with it. I don't know the details of the kinds of operations that go on there, but we intend to broaden our relationship with JPL and get to understand that better. Okay, going on to the next chart. This is a chart that you saw in the earlier discussion. The difference between that discussion and this discussion is we now have Thomas Evans here on our panel, and I'm kind of hitting him cold with our, i.e. Vincent and my description of a vision system, and I'll repeat it here, but then I'm going to ask him for a real-time peer review on what he thinks we've done here. So at the top, we've got the dynamic complex environment that we send robots with manipulators or wheels, or we're in a spacecraft, and we're looking at objects of interest, and we take pictures of them with cameras, and we send images into what Vincent and I have identified here in the blue boxes as being the vision system algorithms at a high level, of course. So the first thing you do is you put some kind of a threshold filter on the image. You lose all the color intentionally, and then you go through a process of extracting features by use of different algorithms to determine what features are present, and then you group those features together and identify an object. And you may have should have some kind of reference information on the nature of the objects that you're looking for. If they're human-made artifacts, then you've got the advantage of having some a priori knowledge on how they were designed, perhaps the engineering drawings. If you're looking for shaped objects that are natural, then perhaps you have some kind of a limit. For example, the cache box on the Mars 2020 rover is going to have some kind of an aperture that you put the rocks in, and so you want to be able to pick up rocks that are smaller than that to get them inside. So that might be a geometric reference that you would have. That would aid you in the object identification. And then the other thing is you want to know where the objects are and what their pose is, so that you'll know how far you have to reach with your arm to pick them up, perhaps, on Mars. And then what their attitude is as far as how you might have to grasp them in order to pick them up. And again, landing on Mars, you'd have some world reference map based on a priori information that would be very accurate, but it would not be as accurate as you would have the knowledge of based on your local camera system. So that would be used as a reference, but it would also be updated. All this would be plugged into a path planning set of equations, either for traversing on the surface if you wanted to command the wheels, or for path planning of a manipulator if you wanted that manipulator to reach, touch, and grasp some object of interest. And then that would be folded into the command generation and execution to energize your actuators. So, having said that, Thomas, what is your opinion of this?
Charlie, that's a good explanation. That's basically the goal of machine vision and how we use it in our laboratory. And a lot of the research that we've done since we started WRTC in 2009 is to develop machine vision algorithms and test those in operations, simulated operations in our laboratory. And ultimately, as Charlie discussed, that pose estimation is our goal objective for a lot of tasks that we work on. We want to be able to determine where that object or feature of interest is, and then use that to control the robot kinematics to either drive to it, perform a task, or drive away from it and avoid collision avoidance. So just to give some background information, that is one area of research that we perform. Like I said, we started in 2009, and we ultimately are partnered with Goddard Space Flight Center, working on a lot of objectives in the robotics area for them. This is driven through West Virginia University. We have several research faculty and professors on our team that do out-of-the-box research, provide low TRL level assessments and development of sensor systems. One of those is machine vision, to drive some of the robotic operations and the missions that we're talking about here today. So if you don't know, our lab is located in the technology park here in Fairmont, West Virginia. And the robot and vision systems we have in our laboratory question that we're going to discuss now is we are located in a large simulation bay. We have multiple robotic platforms. The simulation bay is blacked out with 60 by 80 by 60 dimensions in feet. What we want to do and what our objectives are test in full scale in simulated environments as much as we can on the ground-based operations to mature the technology and support these types of missions. Vision systems, how we've done that so far, I think in the previous discussion, Charlie hit on that well with the system they did here with their interns. We want to be able to develop the algorithms, use the sensor systems that are available to us, whether that's optical cameras, stereo vision pairs, to generate that position estimation. Have a truth system there available to tell us how well our algorithms are performing, and then have a simulated environment to do that and test rigorously to mature that technology. So that simulated environment includes relative dynamics. We have a motion-based platform which could control our target, simulate the motion we'd expect, or relative motion between that and our manipulator or optical system. We also have solar simulator capabilities where we can test and develop in the relative environment and solar dynamics. So all those things are how we mature our technology. And when we're talking about particular vision systems, doing that in the ground test setting with the relative environment increases our TRL in development and gives us a lot of insight into how that system may perform in, say, ARM or other missions with robotic manipulators.
Very good. Let's see, let's go to the, we'll go to the next chart and see if there are any other questions there that you haven't already covered with that very good description. I will have to say I'm very envious of your laboratory up there. It's a fine robotics lab.
So just adding on to that a little bit, some of the work that we've done so far in supporting of asteroid redirect mission is looking at some of the prototype tools that may be used to capture or manipulate an asteroid, possibly if that's put on a more advanced robot manipulator, one that is higher in degrees of freedom, maybe 7 degrees of freedom. And ultimately, if we're driving towards autonomy for those types of operations, the first understanding is what data can you extract? What is that data providing to the logic of the system and the control? And how do you work with it to accomplish a task? So there's high divisions between semi-autonomy and full autonomy. And as far as where ARM is right now, it's still being down selected as far as the sensors that could be used, how much autonomy will be applied, and ultimately, like Andres has talked about earlier, whether option A or option B will be prevalent.
Okay. All right, Vincent, you're not out of the woods yet? Okay. So, given, oh, certainly.
Two questions. One, On these missions, we have multiple sensors. By the way, my name is Greg Blaney. I'm director here at IV&V. We have multiple types of sensors, radar, visual. Are we integrating those? How do we prioritize those if we do integrate them? If you remember back at DART, we had 2 systems. We didn't use both systems, so we crashed into the other vehicle that we were trying to rendezvous with. Probably don't remember that. You probably weren't even born then. But anyway, so if we're going to use visual and radar in various systems, how do we integrate them? How do we prioritize that data and make sure that they're going to work? So hold down the second question for you. We're a quarter-mile apart. Why aren't we working together? So you guys have hardware, simulator, all that kind of stuff. How can we help you provide an assurance case for the software that's going to drive those systems? Maybe we should be able to work together, especially if we're going to use those on real missions. So we'd like to partner with you if we could.
To answer your question, Greg, yeah, there are different kinds of sensors and systems that can provide this data to us. And so the question is, what's the best kind of system for a given application? And then how do you, when you have not redundant, but different kinds of systems providing the same data, how do you prioritize that? And I really think the answer is it's practice, it's rehearsals. So on OSIRIS-REx, prior to the actual sampling attempt, they're going to go through several rehearsals to step by step take perform all the activities necessary to sample from the surface of the asteroid without actually touching the asteroid, and they're going to save the actual contact for the first run through. So during the sampling, there's a couple different ways they're measuring their range and relative position on the surface of the asteroid. They use the GNC LiDAR to provide ranging information, and they also use navigational cameras, which can provide stereo images, which can give you an idea of the surface features you're near, and you can also derive your ranging information from that. So you want to see the software set up to take inputs from either source, and then during these rehearsals, you want to fine-tune, sanity check your data between the two. I mean, because in the end, it's probably best to, at least for the purpose of a mission like OSIRIS-REx, to when you're finally going to do this, choose your one source and then roll with it. So during the rehearsals, you want to see them taking the data from both sources. You want to sanity check it against one another, determine what's the best for your application at hand. I can't really tie that back to DART very well because I'm not terribly familiar with that, unfortunately.
First, Greg, I appreciate your question and the topic about partnerships. Yes, we are favorably geographically close together, and I think it's a great opportunity both for IV&V and WVRTC to look at that opportunity. In general, I think it's a great idea. What we look at on our side of things is full test, and retest, hardware in the loop, understanding the application and possible errors in that sense. But you look at the demand for success from the NASA environment and space exploration in general, the more eyes you can get on a problem with more advanced scientists and engineers, the more sure you're going to be. So we are open to discuss how we can engage in that opportunity in the future.
Good questions, both. Looking at the time, Vincent, I'm going to make a decision and skip you. Is that all right? And we want to open the floor to other questions about any kind of robotic thing. This is a anything robotic question session. So if you want to talk about robotic cars or the robots that doctors put within the human anatomy, or how people recognize faces for crime prevention or detection, open forum here. Mary.
I think I'm going to go right down the line on the panel because I had a couple comments and questions in between. This young man, I feel your pain. We have a similar vision technology in my field. We have them mainly in what we call a CMM, a coordinate measurement machine. Takes the X, Y, and Z coordinates of a part, use them mainly for measuring parts. They come touch, probe, vision, and laser. And it's much like your slide 12, where we, as an operator, would set a plane or say a series of reference points, go in, collect a number of points, construct a feature. We've had challenges with the features as well as the programming aspect of it. In our capacity, we're going out significant figures, say 4 or 5 digits to the right of the decimal point. So these are very, very precision measurements on a part that we regularly produce. We can lock down features in a program and lock it down and tell the engineers this is what you must use when we inspect. Our challenge came, we get parts in from suppliers, say machine shops, and they're custom to a particular patient or their specialty part. And then there's decisions made on both sides. What features are we going to go with? How are we going to program this? And the deviations, if we're not coordinated and working together, can be significant enough to raise a flag or a failure in the part. And it's not the part, it's in what was chosen by the engineers. So it's a tough field. It's tough. And we're in an environment, and here you are out there trying to get this done. So I commend you. It's very tough. I guess tying in with this gentleman, we are in an enclosed environment, much like your laboratory. We do have a light source with the brightness and contrast on our instrument, and I know you said you had cameras on there and a tool turret. Did you think of, in our essence, we have it on a stage where we're able to take care of our lighting problems because we're in a controlled environment, bringing that stage out to your environment. In other words, putting something on the turret or looking into some of the old photography technologies. In other words, I'm trying to formulate this, but instead of thinking in terms of just collecting, how you could bring the stage, like what we have in an enclosed environment, out into your environment.
Okay, when you say out into the environment, are you speaking in space or
Yeah, when
in the backyard here?
When your instrument or your little robot is out collecting, in other words, we'll just do a simplified example. And he's trying to collect. On my instrument, I could collect, and if it's too light, I could make it darker. I could adjust, I could contrast. Right. I could even, make the background darker.
Oh, okay.
He could take out his little arm and say, put a dark screen behind what he's trying to see. Do you understand what I'm saying?
Yeah,
Like
yeah.
Those types of tools.
Right.
In other words, bringing the stage to your
Yeah.
environment.
Yeah. Well, what you would do is you'd augment real light, or natural light with artificial light. Choose a dark day or night, and then you can control with the lights that you provide with your robot, the illumination for whatever you're trying to do.
So you would have an array of lights.
I mean, that would be
different-
one approach.
One approach.
Okay. We're not going to do any of that.
Right. No,
No.
this is just theoretically.
Yeah,
talking,
yeah.
But you know where I'm kind of going.
Yeah,
with it.
but I've got a question from you. When you
Sure.
talk about custom things for patients,
Uh-huh.
I love the idea. What's nagging me, are we talking about things that go inside of people or some kind of prosthetic or something that they
Okay,
they
custom,
use?
when I mention custom for patients, it would be a medical device that goes within a patient.
Yeah, okay,
And the surgeon would take a particular measurement,
Right.
let's say it's a hip socket.
right,
So it would be specific to that patient, and
Okay.
they would make it specific to those. Now, there are other medical devices that are more generic, and they don't have to be as specific. Almost think of clothing. You
Yeah.
could get small, medium, or large, or you could get like a 32-inch waistband. It's one of those, some parts you need that 32 or 33. Other parts, you could go small, medium, or large, depending on
right,
what it is.
right. Or in my case, 2XL, which, and believe me, one size does not fit all. I guarantee you that.
I know. Some of them will say one size fits most. And then this gentleman at the end, you had mentioned thermal sampling, spectrometers. So I assume you're picking the sample up. If you're using a spectrometer up there, it's probably more a quick and dirty measurement in reference to sample degradation because they do the extensive testing.
So
down
the spectrometers are all used prior to the sampling. So the spectrometers are used to just determine the properties of the asteroid surface. Once the sample is actually collected, they're going to use images to ascertain that there's a sample inside the sampler head, and they're going to use a moment of inertia measurement to determine the approximate mass of the sample. but they won't be performing any spectroscopy on the collected sample.
See, that was my question, because, and did they ever consider that? Because there might be, between transport and time, and especially when you're dealing with different chemical compositions.
The answer to that is probably they did, but there was a whole host of scientists that got together and defined what the intent of the mission was, really.
That, and they could have concern, because with the spectroscopy,
Yeah.
you were shooting the light beam through the sample, so
Yeah.
sometimes that can
Right.
impact the sample as well. Okay, great. I thought this was wonderful, and I enjoy your presentations and your proteges. This is wonderful. Thank you.
Thank you. Whoever gets to mic first.
You guys have seen different missions that are using vision systems to perform like flight critical or safety critical operations. Like what missions within the scope that you all know? There we go. What missions within NASA scope that you all know are planning to perform flight or safety critical operations based on vision systems that you know of? Because I mean, the Mars rover might not do that, but OSIRIS-REx might. And the other thing is a comment after your response, but one of the things that we did here at the facility is we did some analysis on the DART mishap, which had 26 contributing factors. So if you, and it was our team that did it. So if you guys would ever be interested, just come see me afterward, and we can set something up and talk to you, because I think there's a lot of lessons from that and a lot of inputs to different aspects of the robotics vision systems that could be applicable. So,
Well, thank you very much for the invite, and we will take you up on that for sure. Now, your first question was which missions have been operated using the closed loop vision?
What ones planned do you guys know that would be using vision systems to perform like mission critical or safety critical operations? Because I just don't know. DART's the only one that I know of that has attempted to in the past, but do you guys know of any that are planning to do that?
Well, I can't tell you specifically other than what we've talked about already. But certainly you walk up to anything that's highly critical, such as life support or anything like that, very cautiously with any automatic system. And vision is just a technique of measuring geometry, and the application of that geometry for a critical situation would have to be, would have to be taken very slowly.
Yeah, okay.
Yeah,
And
right.
I mean, just to clarify, I was just saying like, so OSIRIS-REx might at some point switch to its vision solution to do its final touchdown on the asteroid. That would be a mission critical maneuver.
Right.
So,
And David might have, David might have some words on that.
if you guys knew of any other missions that would be doing something like that.
Yeah, that's a possibility for OSIRIS-REx. Nothing else comes to mind, though, right now.
Mars 2020 might use terrain relative navigation. So when it's coming in to land, the lander might be using to create maps to figure out in real time what is a safe place to land. So it actually might autonomously choose that with a vision system.
I think as well as the DIMES thing that was on the Mir rover's descent, also I think Deep Impact, as it approached its target, used some vision system to calibrate its actual final maneuvers.
Mhm.
That was clearly mission critical too, because if it didn't calibrate, it would have flown past instead of impacting.
Okay.
Following up on a couple of things that were just said, those mission critical aspects that were just mentioned they're not just mission critical, but they're also unlike the OSIRIS-REx, unlike Unlike the OSIRIS-REx, which is a measured approach, and Dave, you walked us through some of the checkpoints and the timeline on that on a CD. Those happen in a measured way. They're relatively slow, and you have ways you can back out of them or retry your approach. Unlike the descent, the Mars descent, or deep impact, where things are happening faster and they're irreversible. I mean, you're going to land, you're going to have your impact. What do you see? Actually, could you go to chart? I think it was chart 12.
Which chart?
Chart 12. What do you see is, and broadly speaking, is the changes or the evolutions that would need to happen to go from the sort of measured approach to the happening in near real-time approach? And I guess you're saying that they're actually going to do that more sophisticated safety analysis, or where is it safe to land, as opposed to DIMES, which Dr. Feather was mentioning, I guess was a little bit easier problem because it was measuring horizontal velocity. It wasn't actually recognizing features that you had to avoid. So I guess to wrap that up, where would you see needing to speed up the process, or changes that you'd actually need to make, qualitative changes in what you do to make that happen?
Feature extraction is definitely, takes up the most computational power to figure out, to correlate, to say that this feature correlates to this feature. So to know, because it's easy to pick out, interesting points where you see corners, but it's really where you see features and how you, because once you extract what feature is where, then your problem is pretty much solved. But the difficult part is determining what feature you're looking at.
So that you need to, that would really need to be sped up. That's one part of that solution is speeding up the feature extraction. Okay. Also,
And might I add, as you're moving, the object that you're looking at is going to change its characteristics based on your point of view moving. And so you've got risk that you may lose the reference that you thought you had because it looks different.
That goes again to the projection,
Yep.
And motion blur.
I guess you're going
Speak right into the microphone. You're really soft.
Okay, you're going to, I guess there's going to be a lot of evolution in incorporating ways the system can know about objects, and as Greg mentioned, different, not just vision, but radar and other things, but eventually even with, I guess, tactile systems for things that are exploring a lunar surface or a planetary surface. So I guess it's not really a question, but a comment. That's going to be an interesting challenge for you in both in terms of incorporating that into the methods for robotic approaches and handling, but also in terms of verification and validation of those systems.
I have a dumb question, but a big voice. I hope that makes up for it.
Okay.
How do you simulate or model or whatever you have to do extreme low gravity, which is I'm expecting you're going to have at an asteroid, versus gravity we have here in your sandbox on Earth? Because I'm assuming that's a long arm and you've got bounce and so on. Because I'm not a mechanical engineer, so I have no idea. It's a really basic question. Thanks.
Okay, wait a minute. You're saying how do you simulate low gravity situations in a one gravity world?
Yeah.
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 Well, for manned space flight, you build a very large swimming pool, and you put people in there, and you do all kinds of complex things there. Of course, it makes them lighter in one respect, but if they turn upside down, the blood still goes to their head because they're still in the 1G field, right? So for any kind of an apparatus you want to try to simulate that, you've got to offset the gravity effect. So you can have stronger manipulators, hydraulically driven manipulators to represent something that's a lot lighter weight in actual space. I don't know, are we getting anywhere near?
Do you have any, I mean, do you have software simulations too? I'm assuming you do.
Software related?
Just to simulate the arm motion and the, feedback from your vision.
Personally,
engine.
Vincent and I do not have that. Within NASA, there are any number of major simulators that have all of that. JSC, Andre down there, Andre ran the engineering simulator at JSC that represented, its history goes back to the lunar module, okay? And so they simulated every spacecraft since. And so, yes, those simulators exist.
I guess I can add on some of the
Does that help?
experience. Oh, sorry, Charlie.
Yeah.
Some of the experiences we had in working with that to get the relative environment as accurate as possible. One of those is a zero gravity flight. If we're looking at a dynamic target, we want to try to simulate that gravity compensation or that gravity vector in there. The target on the 0G term of the parabola was tracked. We got the motion from that from 4 days of flights. From tracking that motion, we were then able to program our robots to reperform that operation so we could track it in the lab over and over again to mature that technology. Yep. One thing I mentioned earlier on in the topic or the presentation was the motion-based platform that we have in our lab that also can be programmed to behave with certain gravity response characteristics, and looking at the compliance and gravity compensation of that are other ways that we do it in the laboratory.
So we're going to take, I think, just one more question. We do have one more presentation before lunch.
All right, well, I guess I'll have to pick and choose then. Maybe my question could be towards OSIRIS-REx. You mentioned measuring the properties of the sample, like the mass and so on, after you've taken it. But I guess at that point, it's a point of no return. You've got your sample. If it's not good enough, you can't go back for another one, right?
Not quite. So unless something on the spacecraft's actually damaged, they have resources for up to 3 sampling attempts.
Okay.
Because really your constraining factor there is the nitrogen. So they have 3 bottles of nitrogen that they're taking on the spacecraft. So if they don't get enough the first time, you really have to weigh heavily whether or not you want to go through the risk of another sampling attempt. But they will have 2 more nitrogen canisters they could use to attempt to collect another sample.
When you collect another one, you add to the sample you've already got?
Yes, because within the sampler head, the sample that you've captured is past a Mylar flap valve. So you would really just be forcing more in there.
Might as well.
Yeah, yeah.
Thanks.
Okay, I'd like to thank our guest, Andre Sylvester at JC. We appreciate your participation, and Dr. Evans here, we appreciate your participation as well as the local guys here. Thanks.
Thank you. Okay, we're going to go ahead and move right on